Hello, my name is Romeo, and today I'm going to be talking about ElectroSpray propulsion. So, what is ElectroSpray propulsion? So, basically, ElectroSpray propulsion is a type of spacecraft propulsion method, of course. At a high level, it works in the same way that all propulsion mechanisms do, by ejecting mass in one direction and creating motion in another, so conservation of momentum. However, compared to other spacecraft propulsion methods, ElectroSpray propulsion provides much less thrust, at least per unit, but I'll touch more on that later. So here is the basic principle of ElectroSpray propulsion. A positively charged liquid, basically a liquid that has mostly ions and very little electrons, is used as propellant and expelled through an extremely tiny needle-sized nozzle. The expulsion is created by placing a negatively charged plate or multiple plates at the tip of the nozzle, causing the liquid to be accelerated forward towards the plate, or even causing just ions from the liquid to be accelerated towards the plate. And these occur at high velocities, and they're then shot out into space. It's pretty similar to electric propulsion system, except instead of just shooting out ions, there's a liquid involved. So the nozzle shapes can vary, but typically they are either a hollow needle-like nozzle, which is basically just a needle with a hole through the center, and the liquid can flow from the storage container through to that hole to the tip of the nozzle. And this is normally done via capillary pumping, so there's an actual pump that's pushing the liquid out towards the tip. Or there are externally weighted needles, which utilize capillary action to draw the fluid from the storage tank to the tip of the nozzle, where they are then accelerated by the electron plate. On top of this, there are three main types of ElectroSpray thrusters, and these just alternate what type of positively charged liquid they use mostly. So like there's colloid thrusters, which they expel charged droplets, and of course they use charged liquids. There's FEEPs, which utilize liquid metals, and they expel positively charged metallic ions. And there's ionic liquid ion source, and these also use positively charged liquids, of course, but specifically, they tend to expel a mixture of ions and charged droplets. So comparatively, the colloid thrusters will expel these charged droplets. FEEPs tend to just expel ions, and then the ionic liquid ion source will extend a mixture of both. So there are some caveats to each design. So like colloids, they have higher mass to charge ratio and higher thrust, but they have lower ISP. And FEEPs and the ionic liquid ion source, they have lower mass to charge ratio and lower thrust, but they tend to have higher ISP. So alone, ElectroSpray propulsion is pretty useless. However, the trick is to combine multiple thrusters into a grid-like or array of thrusters, and that really allows you to have that thrust that you want or the ISP that you want, instead of just having to try and use one single needle. And that really gives you the performance characteristics that you want from this kind of propulsion system.
So there are some issues with ElectroSpray propulsion. So one, it can be kind of bad for proximal operations because you're depositing charged particles or ionic liquid onto the surface of some craft. So like if you're trying to maneuver around, let's say the ISS, and your small spacecraft or whatever spacecraft you're using is using ElectroSpray propulsion as its maneuvering propulsion system, it can be depositing all those charged particles and all that liquid onto the outside of the spacecraft, which isn't very good. Same thing that happens with electric propulsion, except because you have this kind of liquid, you could be really depositing a film of liquid onto these spacecrafts. It's also really hard to manufacture. So these nozzles that the ElectroSpray propulsion use are very small, on the order of like nanometers or millimeters in size. It's really hard to manufacture these systems in a kind of fast production way. So like there are companies that are specialized in manufacturing these propulsion methods, but it's not like really that an undergraduate team at a university can just go into their local machine shop and manufacture an ElectroSpray propulsion system for their CubeSat or something. So what is the current state of these systems? So ElectroSprays are classified as an emerging technology. So only one spacecraft has actually really flown with an ElectroSpray as its propulsion system, and that was the LISA Pathfinder, formerly known as SMART 2. And this was an ESA-led mission, and NASA JPL contributed to the ElectroSpray system in collaboration with Busek. This was not the only propulsion system on the spacecraft as well. So like it also utilized a cold gas thruster as a second control system. So the most prevalent manufacturer of an ElectroSpray system has to be Busek. They provided the ElectroSpray system to JPL for the LISA Pathfinder mission and have been working on designing a commercially available flight version of their ElectroSpray thruster cluster. From their internal research, they have found that ElectroSpray systems can be 2 orders of magnitude more precise than reaction wheel systems, and that when utilized as a disturbance reduction system, so like something to reduce the noise in a system, the position noise of the spacecraft is reduced to the diameter of a DNA helix. so roughly 2 nanometers. They have actively been preparing their system for flight integration and long-term use on spacecraft. Their current research has actually involved developing different variations of their ElectroSpray system, like actively and passively fed systems, and characterizing them and seeing how well they perform. So specifically, they have been working on their BET 300-P ElectroSpray thruster and finding that variations of the thruster could achieve up to 2,300 seconds of specific impulse. Other researchers have been focusing on advancing the supporting equipment of ElectroSpray thrusters. Because they are a type of electric propulsion, they require capable power systems to ensure optimal performance. Researchers at Charles III University of Madrid have been advancing the field by developing a high-efficiency switching power supply, allowing for the ElectroSpray system to utilize the spacecraft's bus power for their high-voltage application. Their system performed with 90% efficiency in the 2 to 10 watt and the 1 to 2 kilovolt range, which is the desirable voltage range for ElectroSpray thruster systems. Impressively, their system only weighs about 39 grams and fits into a 42 by 42 by 25 millimeter cubed volume, which is ideal for CubeSats and other small spacecraft that their design is aiming to support. Their system also utilizes feedback control to allow for the setting of different voltages and, of course, monitoring the system. Now, there has also been research that has been looking into how the orientation and layout of multiple ElectroSpray thrusters affect the overall performance of a spacecraft. Specifically, a team from Northwestern Polytechnic University have been looking into the effects of non-uniform thrusting of combined ElectroSpray thrusters. Of course, non-uniform thrusting is detrimental to the overall control and performance of the propulsion system, but looking into how impactful it was, as well as ways to improve it, can benefit future spacecraft utilizing this technology. The team found that at lower voltages, the thruster displayed non-uniform emissions. However, upon increasing the voltage, the emissions began to become uniform. The results of the study also suggest that ElectroSpray thrusters should have their voltage flow characteristics parameterized to better understand the performance of the thrusters at low voltage. They also found that reducing the flow resistance in the nozzle helped the thruster perform better at lower voltages. Now, because ElectroSpray systems are desirable for their precision thrust and maneuverability, the longevity of these thrusters can greatly impact a spacecraft's mission life. So another aspect of the field of research is looking into the lifetimes of these thrusters as well as how to improve their lifetime to enable longer missions. So a team of researchers from UCLA and working with NASA JPL were looking into what causes lifetime reductions of these thrusters and what can be done to improve it. For many ElectroSpray propulsion systems, the buildup of propellant liquid on the emitter, so on the needle and the negatively charged plate, are big factors in the longevity of the system. Things that accelerate this buildup can be misalignments of the negatively charged plate and the emitters. So like if the negatively charged plate is slightly offset from the emitters, and the actual hole size in the negatively charged plate. So like the little bores that the actual liquid flows through, which of course makes sense. The research team found that by adjusting the hole size and adjusting the grid spacing, or the spacing between each nozzle and each hole, the lifetime of the ElectroSpray system could be increased by 200 to 400%. They also analyzed the impact of misalignment, finding that it can lead to up to 20 to 50% lifetime reduction. However, the research team found that increasing the hole size also led to more electron backflow, as in the electrons started flowing towards the needle rather than the ions flowing away from the needle towards the electrons. They proposed that increasing the voltage bias between the nozzle and negatively charged plate can help decrease the amount of electron backflow, which of course, though, would require more power. And since ElectroSpray propulsion systems can take different forms, there is a question of whether the different types can be combined, as in combining colloid or ionic liquid ion source propulsion systems. One research team from the Royal Military College of Canada has actually looked into combining ion-emitting and droplet-emitting thrusters. And of course, these would both use the same ionic liquid serving as the base. And they wanted to see what kind of performance characteristics are brought by the system. So the droplet propulsion system, they found, has a much higher thrust, of course, because it's emitting more mass, while the ion emitter had much greater efficiency. The team also found that the pure ion emitter had roughly 4,040 seconds of specific impulse, while the droplet emitter had about only 140 seconds of specific impulse. The pure ion emitter, however, had about 0.14 micronewtons of thrust, while the droplet emitter had 10 times that much at 14 micronewtons. Of course, that's not a lot. That is per needle. And while they're still small, for spacecraft adjustments, the two systems could be combined to allow for better positioning control. So like you could use the droplet emitter to do higher movements or bigger movements between your spacecraft positioning, and then do micro adjustments using the ion emitter. So then what are the applications of electrospray propulsion? Clearly, electrospray propulsion shines as an attitude and orientation control system. While low thrust, the high ISP provided by these systems and the precision thrust capability allow for precise positioning, especially for smaller sized spacecraft like CubeSats and nanosats. Of course, this opens up the spacecraft development field to small organizations like student clubs and startup companies where they can utilize small attitude control systems like electrospray thrusters. So overall, the emerging technology of electrospray propulsion seems to be providing a better, more precise propulsion method for future spacecraft. While there are definitely issues to address, such as the particle deposition onto spacecraft hulls, the overall charge of the host spacecraft, longevity, and the manufacturability. As I said before, the precision and size afforded by these electrospray propulsion systems make it worth researching and developing for future spacecraft.